Got it.
Are we on?
Yep. Yeah, I know, it's fine.
All right, gang. Now, I know my friends who are watching, I'm sorry. Varun, go ahead and pan around so we can all see who's in the class. Hi. All right, well, we got the tops of everybody's heads. Varun is the master cameraman, but yeah, if you really want to have faces on the
Varun, you suck.
Anyway, this is 4th hour AP Chemistry, and some crazies in here.
We're the craziest class ever.
I know this is a different audience than the last time we had to film in here, so I do apologize in advance.
Did you bleep out the swear word from the last one?
Wait,
Yeah, no.
did you cut it? Because I was trying to find it, and I did not find it.
That's because it didn't happen.
Yes, it did.
All right. If I could have your attention, please. Number 55. The question is, if you have a reaction that has just the one reactant, A yields products. It's about successive half-lives. Starting with an initial concentration of 0.1 molarity, it says that the first half-life is 10 minutes. That means in 10 minutes, the reaction goes from 0.1 molarity to 0.05 molarity. That's what half-life means. It's how long it takes to get to half of the original concentration. But then it says, talk about successive half-lives. So then after 10 minutes, then the next half-life starts with an initial concentration of 0.05 molarity down to 0.025 molarity. Does that make sense? That's what the second half-life would involve. Yeah. The first half-life went from the initial 0.1 down to half of that, 0.05. Then the second half-life goes, now 0.05 is the initial half-life for the second half-life, to 0.025. How long does that take? 20 minutes. From 0.025 to 0.0125, that takes 40 minutes. What order is this reaction? Is it zero order, first order, second order? Now, I know some of us have already talked about it, but for zero order, the half-life equation is A0 over K. Is there a 2 in there?
Yeah. Wait, no. No, there isn't. Wait, there is. It's 2K.
I don't remember what these are.
It's 2K.
It's 2K.
Yeah. Over 2K.
Okay, and then first order is,
ln of 2 over K.
I know this one is ln of 2 over K.
Yeah.
And then second order is
1 over K.
1 over K. There's no 2 in this one, right?
No.
Thanks. Okay. I mentioned this when I first talked about half-life, and I now want to mention it again, now that we have something concrete that we can look at. For zero order, as the concentration gets cut in half every half-life, this number is getting cut in half every successive half-life. What's happening to the half-life? It's not staying the same. This number is getting cut in half, so what's happening to that number? It's getting cut in half as well. If you cut the numerator in half, that means that the fraction is going to get cut in half. So every successive half-life for zero order gets shorter and shorter. For first order, there is no term for initial absorbance. Still working on the last lab. There is no term for initial concentration. So the interval for first order is the same every time. It doesn't change. For second order, the initial concentration is in the denominator. So as the initial concentration gets cut in half, what's happening to the half-life?
It's getting bigger.
It's doubling. It's getting longer. What's happening here? The half-life is doubling every time. What order is it then?
Second order.
Right. Can you find the K value
Totally.
from this equation?
Yeah.
You know the first half-life, and you know the initial concentration. So you can find the K. Then the question asked you to find the concentration of A with that starting concentration at different times. So you're going to plug into the second order integrated rate law and solve. Solve for, well, you know the left side of the equation is 1 over A. You're going to solve for that A. Sophie?
I use the integrated rate law, and I
Yeah. Did I say to use the differential?
I mean, yeah.
You have to use the integrated rate law. If I said differential, that was wrong. It's the integrated. Yeah. You have to. You can't use the other rate law because the other rate law doesn't have time in it. Anytime you're dealing with time, you have to use the integrated rate law. Anna.
Okay, I got A, but for B, it says that 30 minutes is like 2 successful half-lives, and I don't get that.
Successive?
Yes.
Well, yeah, because the first half-life takes 10 minutes. The second half-life starts at the end of the first half-life. So 10 minutes for the first half-life, 20 minutes for the second half-life. That took a total of 30 minutes. So yeah, it got cut in half twice. It's going to go to 0.05 then 0.025. That's the answer.
No, because 30 is between 20 and whatever.
Yeah. I see what you're saying. Yep. Yes, ma'am.
For like first order, why is there like no change here?
Oh, because the half-life doesn't depend on what the concentration is. And that's the only time it doesn't is for first order. So if you're cutting the concentration in half after the first half-life, that number now is half of what it was in the first half-life. So that affects that. This one is independent of the initial concentration.
So the T is just random numbers?
No, whatever the K value is, you can solve for the K, take natural log of 2 divided by K, and that would be what the half-life is every half-life. So after the first half-life, the second one is going to take as long as the first one did. Not seeing that?
I'm saying that, but then I can't apply to the zeros. It's like if then it's the same thing for like I don't know. It takes as the same time for them to change or something.
The first half-life, let's just throw a number out there. Let's say that T1 half equals 10 seconds. So it takes 10 seconds to go from 0.1 molar to 0.05 molar. That took 10 seconds. Then, to go from 0.05 to 0.025, it takes another 10 seconds. Then to go to 0.0125, takes another 10 seconds. So the half-life doesn't depend on how much you start with. It's just the same interval every time. That's what first order means.
And then for the second, it's just not.
For second order, yeah, that would take 10 seconds. That would take 20 seconds. That would take 40, like that. That was number 55. Was there a no? That was it. There's one last topic in the chapter. I want to make sure I got this in. Tomorrow we're going to spend our entire hour looking at the lab, doing the lab, trying to do the calculations for the lab. The lab is going to make you busy. However, when you're done with it, you're going to look back and say, "Oh no, that wasn't bad." The lab's going to be due tomorrow at 3 o'clock. So you're doing the lab tomorrow, and it's going to be due tomorrow. You're not doing a write-up in your book, though. You're just going to do it all on the handout.
Oh, so we don't have to have like the quiz or anything.
Right. Just going to fill out a handout.
So like the first slide we did that.
Straight. Yes. Question is, could this lab also be on the quiz? Might be. All right. So here's the deal with catalysts. You have all worked with catalysts before and learned about them. I know in biology they talk about enzymes being catalysts, and you know the general definition of a catalyst. It makes a reaction go faster. Well, what does a catalyst do in order to make the reaction go faster? Yes?
It helps orient the molecule and it decreases the activation energy.
Maybe it orients the molecule, and yeah, it would often disrupt the mechanism, cause the reaction to go through a different mechanism with a lower activation energy. Lower activation energy always makes for a faster reaction. Is that okay, Vern? Yes, I'm done now. Yep. There were a couple people. I think they were in this hour. Oh, maybe they weren't. that I didn't get it back from. They were last hour. I forgot to ask you.
Ask them.
For the lab. Good idea.
What are you trying to say with the thing at the bottom?
I'll show you with an example.
Okay.
Is that you? Okay, doesn't bother me. You're nervous? What? You might want to.
Wait, they're updated already? Oh, okay.
Why is he? Why is he
Like that whole is K
The rate law. The rate constant, yeah.
yeah. So then put the rate would be valid. Wait, what's the actual?
You can't get the actual rate unless you do the differential rate law. You can plug the K value into multiplied by the concentration. You have to know how to do it.
Oh, because that's the your mom got
Yes.
like,
Yes.
he said that her mom got a constant tag of like,
You know how the differential rate law says rate equals K times concentration or whatever? That's what gives you the rate. That integrated rate law only tells you how the concentration changes with time. So it's about
The struggle of having
data.
braces.
Integrated rate law is about the data, where the differential rate law is how fast.
Invisalign braces.
Oh, okay. I'm going to go off of this slide. I don't know if this is one of the assigned problems, but I want you to look at number 75 at the very top of the board up here. This is a mechanism, a two-step mechanism. They have added the two steps together to give the overall reaction. Based on what I wrote in the parentheses in the slide, what would be the catalyst? There is a catalyst in this one. Which one is it?
No, ozone. No,
What, Mohammed?
no, no, wait.
NO.
Oh.
NO is right. Why?
oh, I get it.
It's in the
75, yeah, this one.
Oh, I get it. Oh, okay.
NO is added as a reactant, isn't it? At the beginning, you put ozone with NO, and the reaction starts. You also have another thing in there. You have to add oxygen atoms, too. Oxygen, the non-diatomic oxygen. So you have to have some cylinder with ozone in it, put it into a vessel, and then you have to have some cylinder with NO in it and put it into the same vessel, and then you have to have the oxygen to put in there, too. And these things all react, and you're going to get oxygen gas, O2. What happens to the NO?
It recycles.
It kind of recycles, doesn't it?
Yeah.
The amount of NO that you added at the beginning is still there at the end. It did get involved in the reaction and temporarily changed, but then at the end, it was NO again. Are you with me? That's what happens with a catalyst. A catalyst will get used in the reaction, but then it'll be remade by the time you get to the products. So it's there, but it never gets used up. So therefore, a catalyst is not really a reactant, because a reactant gets changed. This only got temporarily changed, and then it was there at the end. Now, there's also an intermediate in this thing. And sometimes people confuse catalysts with intermediates. What's the intermediate in this reaction, Artia?
NO2, but can I ask something?
It was NO2, that's right. Because